So in a future video, I will talk about a metric space that resembles the picture of the binary tree that I have tried to draw here. And before going into that, already the set theoretic aspect of this looked interesting to me with some links to other quite standard stuff. So I wanted to do this video first. I want to begin by asking the following question. I give you two sets and I ask you to think about which one is a larger set from the point of cardinality. First, the set of leaves, the ends, if I can say, of an infinite binary tree. So you start with one node, let's say called the root, and then you go to next two, here and here, and then each one of them produces two children, and then you repeat the process countably many times. And a leaf can be defined precisely, in fact. And so, for example, we can say a leaf is a sequence, an infinite sequence of lefts and rights. So to each node we can talk about the left child, the right one, left and right of this one, left and right of this one. So to reach a leaf, a point that is waiting down here, all you do is you choose a sequence of so it seems like here you will go two rights, three rights, maybe then a left, and then who knows, maybe left, right, left. So any such sequence uniquely identifies a leaf. And the uniqueness is if you change any of these R's or L's to the other one, you will for sure end up in a new point. And that's actually part of the proofs that we will see. The second set we're talking about is the set of all finite subsets of n. So this is not the power set of n. For example, the subset of all even numbers is not included here. So we insist on finite sets. So 1 and 2 is a member of this set. 1 until 100 is a member. So any finite collection of natural numbers is a subset of this, is a member of this set I'm talking about, but not any sequence that has infinite, any set with infinite cardinality. Anyway, so think about all the possible subsets of natural numbers with finite elements in them. And think of that in totality as one set. So here we have set described in B, and I described the set A. Which one of these has more elements in it? Which one is bigger in terms of cardinality? The answer is A. A is uncountable, or we can say A is as a set of the same cardinality as the real numbers. On the other hand, the set B is indeed countable, and its cardinality is the same as cardinality of all natural numbers. So let me give a quick proof of B first. So B is the union of such sets. So subsets of n with at most k elements. Well, let's also just say with k elements. And then if you do k from 1 to infinity, this gives you your set B. So we first list all the subsets of natural numbers with just one element. That will include 1, 2, 3. So a copy of n, like for each number, so you have one subset of one element. So all of them. And then you list for k equal 2 those that have two elements. That will include 1, 2, 1, 3, and then you exhaust all natural numbers. You come back now 2 and 1 is already counted. 2 and 2 is not a new set. 2 and 3, 2 and 4, and you continue like this. And once you do this with 1 and 2 and all of the natural numbers, now you will start with k equals 3, all 3 element sets, and so on. It looks a huge list at the beginning, but we have seen many examples of seemingly large sets being just as large as natural numbers. Well, now to see, let's call this set here bk. So to show that b is countable, it's enough to show that bk is countable. Because countable union of countable is again countable. On the other hand, we can easily see why bk is countable, because bk is isomorphic to natural numbers 2 power k, which is just a1 ak such that each ai belongs to natural numbers. And this is just a finite product of natural numbers, and that in turn is homeomorphic to just natural number, all standard things from basic set theory. So that proves that the set B is actually not that big, only countable. Now, the proof that the set A is uncountable, many of you will have already recalled the sequences here and how Cantor was the first person to prove that the set of all such strings is uncountable by his now super famous, but still doesn't take any of its ingenuity away, that just amazing idea of how to prove that such a set of all strings cannot be counted. And the idea is that whenever you produce any set, so A is uncountable. Rather, I want to prove A is not countable, which then by definition means it's uncountable. So suppose x1 is one sequence of left and right, x2 is another one, x3, and so on. So you make a countable list of strings is a sequence of strings of character R and L. Also, it includes all R's or all lefts. Consider a new element. A sequence constructed as follows. If first letter in x1 is R, then the first letter in y is L. So if you see an R here, make it left, and if you saw an L, make it the right. So this will guarantee in future that the sequence we construct will not be equal to x1, because already in the first letter they disagree. So if the second letter in x2 is R, then the second letter in y is left, and vice versa. So you choose the second letter to be different from the second letter of x2, and you keep going. Now, of course, you can argue like in the deeper level, is this even a valid way of constructing an element? Is this logically, from not logic of mathematics, of course, and based on axioms, a valid way of constructing things? Personally, I don't care about these things, axiom of choice and things like that. I know like it's a serious thing, but I'm on the group of mathematicians who just believes in axiom of choice. And I don't know if this construction really requires such a thing or not. But anyhow, if you believe that this is a valid way of constructing a sequence Y, if you believe that this does produce a well-defined sequence Y, will not be in the set x1, x2, and so on. So we started with a countable sequence of strings, and we produced yet another string which is none of them. We cannot enumerate, we cannot list the set of all binary sequences. So that was the Cantor's, that is famous Cantor's diagonal argument, because you look at this one and then the second letter in the second one and the third one in the third one, so you move diagonally down and you construct a set which is not equal to any of them, because at least in that ith string it differs from xi. This is actually closer to Cantor's original argument than this is what he proved, but then people have twisted things a little bit around and said that this is how you prove that the real numbers is uncountable. Of course, you can do so by saying that, well, every number has a representation with zeros and ones, which are basically lefts and rights, and then the same argument goes through. But to Cantor, he just wanted to find a set that is not countable, and he didn't necessarily just want to prove that the real numbers were uncountable, just any set that was uncountable, and this was his proof. Now, going back to the picture, actually, this has a nice interpretation. So, a string of left and rights, as we said, is a leaf down here. So there is a particular choice of lefts and rights, which will lead you to that leaf. And now we have a countable list of them, so that means we have countable selection of path through this tree, which land in different points. The proof down there is, if we reinterpret it in this picture, is describing how to construct yet a new path which will not land in any of the previously chosen leaves. And the argument is, okay, look at your first path. Does it take left or right? If it took right, then you move to the left. Now look at your second path. Does your second path choose left or right in the next sequence? So it chose right here, so you will choose left, and so on. So this way, you will end up choosing a path which at every stage disagrees with one of the previously chosen paths. So ultimately, the green one you have chosen will be very different from each and every one of the previous ones. So you will end up in a new leaf. So that's for that. But I want to also go back to proving B again using this idea. So how can we really, these are proofs, of course, but sometimes proofs are not really enough. You want to have compelling geometric intuition as to why something is the way it is. So the way I look at this is, how do you choose a sequence of, how do you choose a finite subset of natural numbers? So here's another way of doing it. So you list them, and then the way to choose a natural number is to go over each one of them and then decide if this is going to be inside the finite set that you're going to construct. So we're going to construct a finite subset of natural numbers. What I do is I decide, is 1 going to be in or out? Well, let's say 1 is going to be in. O is out, so we don't choose that. 3 is in. Okay, 3 is in, so 3. 4 is out. No 4. 5 is out. 6 is in. So, and so on. Now, this then is now analogous to exactly up here. So we're making a sequence of binary letters. So in, out, left, right, left, right. So how come that this set is smaller than this set? The point being is that to have a finite subset, you have to make outs from some point on. So all of them will be out after some threshold, because otherwise you will end up with an uncountable. I mean, with a not finite subset. So the last one here, for example, was 6 is in and everything is out. So here we're looking at all binary sequences whose tails are already like decided. You have no more choices after threshold. So only in finite time you make a binary sequence and then you kill all the others. Whereas in A, you keep having this choice of ins and outs for eternity. If you follow the same proof for the counter example, if you follow the diagonal argument, the thing is that the new element you build will not be among these. So if you go through that argument, then after some point, all of these will be in. Okay, you will make a new sequence, which isn't any of the previous ones, but the object that you produced, this y, is no longer in the set of interest. In this case, this new element y that you have constructed, it is true, it's none of the elements in B. However, it's not also among the admissible objects that we're looking at, because this will produce a subset of natural numbers with infinite elements in it. And if you were paying attention, you can see that if we drop this finite thing, then there is exactly a bijection between these two objects. So the set of all the strings left and right, the set of all leaves of a infinite binary tree, are in one-to-one correspondence with the set of all subsets of n. If we, of course, drop the finite case, again here, we drop the requirement that after some point all of them will be O. I hope this brings back some good memories from early bachelor's mathematics courses, but I have, in discussing this, also answered the following interesting question. Why does the counter diagonal argument prove that Q, the rational numbers, is uncountable? The claim, of course, being that you do the same. You make a list of rational numbers. Let's say everything represented in the binary system of 0, 1s, and then you produce this new element y, which is again constructed out of 0s and 1s. And by construction, it's none of the previous things. So you have produced a new element. True, you have produced a new element, but the new element is not irrational, which doesn't then contradict the rationality of Q. So you haven't violated the claim that you can list all rationals. You have find some number which isn't among your list, but also it's not rational. So the new element produced by the diagonal argument is not rational necessarily, because to reach a contradiction you would need to say, okay, this is another rational number which was not in your list, so you cannot make a full list. But the point is, that's not a counterexample to that. Okay, so what we will do in the future video that I mentioned at the beginning was we will go back to this object. I say this is the artist impression because I haven't yet talked about any distance or metric structure on this space, but the thing will be that all these edges will have the same length, say length 1, and I had to do an artist impression, an imprecise picture of what is actually behind this, just to be able to fit it into being able to draw here. So it's an abstract thing. So you start with a point, and then there are 2 points that are its children. Mathematically, you can make all of these make sense, but just so you know that this picture is not necessarily accurate, and we will also talk about the question of whether it is ever possible, in fact, to draw a binary, infinite binary tree inside the plane with respecting the distances at the same time, because here if you do it, it appears that the distance is getting shorter, but in reality, as I said, all the edges have distance 1, every node is distance 1 from its neighbors, and so on. Okay, so until that video, have a good one, and please write in the comments anything you can add to this wonderful isomorphism and the way of looking at these sets and their cardinality. And one last request, please subscribe if you have not yet done so. More fun videos coming very soon. Thanks a lot.